The GBU-57B Massive Ordnance Penetrator, designed for deep penetration strikes against the world's most fortified underground facilities, is now at the center of U.S. strategic airpower modernization. Following its recent operational debut in a complex, multi-phase precision strike carried out by B-2 Spirit stealth bombers, the weapon's relevance and technological evolution have taken on new urgency. The operation, which involved deploying 12 GBU-57s across 2 exact impact locations, demonstrated not only the bomb's immense kinetic force but also its sophisticated targeting adaptability through programmable fuzing, inertial guidance, and platform coordination. This mission validated over a decade of engineering development and operational planning focused on maintaining conventional dominance in deep strike scenarios without crossing into strategic deterrent thresholds. The B-2 Spirit, a stealth strategic bomber known for its ability to evade sophisticated air defense systems and operate globally with minimal detection, served as the sole delivery system for this operation. Each B-2 carried 2 GBU-57s internally, protected by the aircraft's radar-absorbent airframe and advanced electronic warfare systems. Operating in formation with other B-2s, the bombers flew a long-range sortie using low observable routing and GPS-guided precision timing to ensure that each munition arrived at its programmed impact point within a specific time window. Despite the extremely high mass of the weapons and the aerodynamic challenges of carrying such ordnance, the B-2 maintained mission integrity, successfully delivering all 12 bombs within a coordinated strike window. The unique value of the GBU-57 lies in its ability to reach critical infrastructure buried beneath layers of reinforced concrete, rock, and steel. While traditional bunker-busting weapons are effective against moderately hardened targets, the GBU-57 was engineered for exceptional penetration depth and survivability during impact. The munition's hardened casing and massive weight generate kinetic energy that allows it to drive through earth and hardened construction before reaching its detonation point. The system's internal components, including its fuse and navigation hardware, are shielded to survive these extreme forces. The KMU-612 tail kit provides in-flight correction using GPS-aided inertial guidance, allowing for high accuracy even in degraded navigation environments. These capabilities were proven during the mission, where each bomb's trajectory, speed, and angle of descent were tightly synchronized to achieve optimal penetration depth and internal detonation positioning. Post-operation analysis by the U.S. Air Force and Department of Defense confirmed that the strike caused significant disruption to the underground target's functionality. More importantly, it provided a live operational case study that is now being used to inform improvements in both the weapon and its delivery platform. Within days of the strike, the Air Force issued an official request for industry proposals aimed at advancing fuse technology, expanding tail kit production, and ensuring sustainment of all MOP-related systems. These next steps reflect the urgent need to incorporate real-world combat feedback into ongoing upgrade cycles. Specifically, the Air Force is focused on advancing void-sensing fuse systems that allow the bomb to detect internal chambers, adjust fuse delay dynamically, and detonate at the precise moment when maximum structural damage can be inflicted. The service is also seeking suppliers capable of manufacturing more robust and scalable variants of the KMU-612 tail kit, particularly the EB version that includes upgraded navigation and flight control features. These components must meet extreme performance specifications and operate under some of the harshest physical conditions experienced by any conventional munition in the world. In addition, life cycle sustainment, including tail kit retrofits, engineering support, component obsolescence management, and long-term reliability testing, are all being evaluated to ensure that the weapon remains available and operationally ready for the foreseeable future. The B-2 Spirit continues to evolve in parallel with the GBU-57. Its recent upgrades under the Spirit Realm program include advanced threat detection systems, secure communications enhancements, open mission system architecture integration, and modular software support that allows faster updates to mission profiles. These improvements make the B-2 not only a survivable platform but a smart, reactive one, capable of receiving new targeting data mid-flight and reprogramming its payload deployment profile. In the recent operation, this capability allowed mission planners to adapt bomb release parameters in real time based on in-mission intelligence updates, weather conditions, and navigational accuracy assessments. With potential adversaries continuing to invest in deeper and more sophisticated underground structures, U.S. planners recognize that the capabilities of the GBU-57 must remain ahead of any countermeasures. This includes not just increasing the physical penetration capabilities of the weapon but also integrating intelligence-driven adaptability, enhanced data fusion, and fuse logic that can operate in the absence of perfect structural intelligence. One area of exploration is layering internal sensors inside the bomb to detect acoustic anomalies, floor transitions, material shifts, or temperature changes that would indicate structural depth. Such sensors could work alongside void detectors and inertial reference systems to provide a layered estimate of internal positioning, thereby giving the weapon the ability to independently determine the most destructive detonation point. Longer-term planning is already underway for a follow-on system under the next-generation penetrator program. While the full details remain classified, this future system is expected to offer similar or greater penetration performance with enhanced modularity and adaptability across multiple bomber platforms. It may include powered flight capabilities for standoff delivery, as well as advanced targeting integration through data links and artificial intelligence-assisted mission planning. However, until that system is fielded and fully integrated, the GBU-57 remains the only conventional option capable of delivering this kind of strategic effect. Strategically, the weapon reinforces the credibility of U.S. precision strike capability. It allows the U.S. military to address emerging threats located in hardened facilities with conventional firepower, without having to escalate to higher strategic options. In doing so, it fills a unique role within the broader force structure. Its combination with the B-2 Spirit's unmatched penetration and global reach creates a pairing that remains highly relevant in today's rapidly evolving security environment. As adversaries analyze the implications of the strike and likely begin modifying their underground architecture, the U.S. continues to modernize both the weapon and the aircraft that carries it. Lessons learned from the operation are being applied directly to production refinements, guidance system upgrades, software improvements, and mission flexibility. The GBU-57, fielded in relatively small numbers, is a weapon that depends on absolute precision, extraordinary force concentration, and technological overmatch. Supported by the stealth, resilience, and flexibility of the B-2 bomber, it remains a singular tool in the U.S. arsenal for conventional operations against the most fortified and well-defended targets in the world.